طيب اوكي شباب السلام عليكم. Let's continue solving some problem on the application of the first law of thermodynamics for closed system. Here is example number 6. We have a rigid tank is divided actually into two equal partitions. So we have a rigid tank. This rigid tank is just divided into two rigid equal partitions. So the volume is just divided actually by half, and this is actually a rigid tank. So if we need a problem, we have to decide about the system type, either closed or open. So rigid tank, that means the system is closed in this case. Type acid, this tank actually contains 5 kilograms of water. So the working fluid in this case is water. So I'm going to use the steam tank. So this part actually, half part of this actually rigid tank contains water. So this is actually water. The mass of water, M, is equal to 5 kilograms. This water is just occupying half of this tank, and we have a kind of diaphragm is separating actually this water from the other part, which is actually evacuated. Evacuated, that means actually it is under very low pressure. Pressure actually in this case is close to the absolute vacuum pressure. Okay, and there is a diaphragm that separates the water from this evacuated part of this tank. This water is existing at pressure B1 is equal to 200 kilopascal, and the temperature T1 is equal to 25 degrees C. Okay. The other side, as we said, is just evacuated at pressure, very low pressure in this case. Now, if we remove or crack this diaphragm, so in this case, actually, water will be expanding to the very low pressure region. So in this case, this pressure, we are expecting actually this pressure of water to be reduced in this case. And in this case, actually, said the water is occupying the whole volume of the tank. So in this case, the volume V2 is double the volume of V1 because water was just occupying half of this tank. So the volume of the tank, which is V2, is double V1 in this case. And he said actually due to this, after cracking this diaphragm, the water will be allowed to expand to very low pressure, so the pressure will be reduced. And we expect in this case the temperature is also getting down, is reduced. But he said we'll be adding heat, so heat will be added to the system in order to keep the temperature fixed. So the final temperature T2 will equal to the same as T1, and it will equal to actually to 25 degrees C. Okay. We need to calculate here. We need to calculate the volume of this tank, which is the volume V2, which is double V1. We need to calculate also the final pressure of the water inside this tank, and we need to calculate also the heat transfer Q out of this process in order to keep the temperature fixed at 25 degrees. Okay. Then what should we do in this case? So we need first of all to calculate the volume. We have mass of water is given in this case. The mass given at state number 1, which is equal to 5 kilograms before the expansion. This is a closed system, so we expect the mass to be constant. And in this case, actually, the condition of water at the initial state, B1 equal to 200, T1 is equal to 25 degrees C, and the volume is half of the volume of this tank. Okay, so let's take actually this given at state number 1. Pressure is given and temperature is given in this case. So with this value of pressure, we can just use table A5. I will get actually the saturation temperature, T saturation. You can compare the saturation temperature with the given temperature. You will find in this case that the temperature T1 is less than T saturation. So the state in this case actually is subcooled, and in this case, as it is subcooled, I have to use table A7. Okay, but when you look at this pressure value, pressure B1 is 200 kilopascal. So the pressure B1 is 0.2 megapascal. And the first table actually in table A7 is starting with pressure equal to 5 megapascal. So that means at 0.2 megapascal we don't have table in this case. But we have seen when we discussed how to use the table, we said actually if we don't have subcooled table, then in this case we can assume all properties are equal to the saturated liquid properties as the given temperature. So in this case at T1, we can just go to table A4, and in this case actually we can get the specific volume V1 will equal to V fluid in this case. If you go to table A4 with the temperature T1 which is 25, then in this case we can get V1 which will equal to V fluid will equal to 0.001 meter cube per kilogram. Also, we need to calculate the heat transfer of this process. We will need actually the internal energy U1. So the internal energy U1 will equal to U fluid at this given temperature. If you look at this value, U fluid at temperature T1 equal to 104.83. 104.83 kilojoule per kilogram in this case. But what we need is we need to calculate actually the total volume of the tank, which is double of the volume V1. But we have a specific volume V1. Specific volume sugar is equal to the total volume V1 divided by the mass. Specific volume, the mass actually is 5 kilogram. Then we can calculate actually the volume, the total volume V1 will equal to the specific volume 0.001 multiplied by 5 will equal to 0.005 meter cube. But the volume of the tank after just cracking the diaphragm, then in this case water will be occupying the whole volume in this case. V1 is half of the volume of the tank, so the volume of the tank will equal to double V1, which divided by 0.005, it will equal to 0.01 meter cube. And this is actually the whole volume of the tank. Okay. But we need to calculate the final pressure V2. The temperature kept constant. We have the temperature T2 is equal to 25 degrees C. But we need another property in this case. What is this property? So at step number 2, we have the temperature T2 is equal to 25 degrees C. But we have the volume V2, which is double the volume V1. After expanding, the water is expanding actually to occupy the whole volume, which is equal to the volume of the tank, which is equal 0.01 meter cube. But actually we cannot use the volume, we need the specific volume in order to go to the table. So the specific volume V2 will equal to V2 divided by mass, which is 0.01 divided by 5 in this case. And we can calculate the specific volume V2, it will equal to 0.002 meter cube per kilogram in this case. Now at step number 2, we have in this case the temperature T2 is given, is equal to 25, and we have the specific volume V2 is equal to 0.002 meter cube per kilogram. I need to calculate the final pressure, so given the temperature and given also the specific volume, so in this case what should we do? With this pressure, I will be going to table A5, then I will get the value of a specific volume V fluid, the value of a specific volume V gas, and compare them with the given specific volume. So if you do so, you will find actually that the specific volume V2 is greater than V fluid and less than V gas in this case. And the state in this case should be saturated mixture in this case. And under saturated mixture condition, while the phase change process, in this case, the temperature is equal to the saturation temperature, and the pressure in this case will equal to the saturation pressure at this given temperature. So from the table, at this temperature, table A4, so from table A4, then in this case, we can get actually a temperature equal to 25, we can get the saturation pressure. If you did that, you will find the saturation pressure here is equal to 3.1698 kilopascal. Okay, and this is actually the pressure B2 in this case. Okay, that compares the pressure شباب. The pressure B1 was equal to 200 kilopascal before removing the diaphragm. Removing the diaphragm in this case, so the water will be allowed to expand to the low pressure. So its pressure will be reduced in this case. Now the pressure has dropped down actually from 200 kilopascal to 3.169 kilopascal in this case. Okay. طيب, under this condition, we need to calculate also the heat transfer. So in this case, to calculate the heat transfer, we have calculated the internal energy U1. We need to calculate also the internal energy at the final state. Then we can apply for a closed system Q minus O will equal to delta U. So we need to calculate the internal energy U2 in order to calculate the heat transfer out of this process. Okay. But in this case, we need to calculate what? To calculate the internal energy, the state is saturated mixture. So the next step in this case is to calculate the quality of the mixture X2. Given the specific volume V2, and in this case we have V fluid and V gas from the table, and the state is saturated mixture, so we can say X2 will equal to V2 minus V fluid divided by V gas minus V fluid. The value of V gas and V fluid we can get actually from at this given temperature. This is table A4 journal. So from table A4 we can get actually the value of V fluid and V gas. Then we can substitute to calculate the value of X2. If you calculate this value, it will be 2.3 multiplied by 10 to the power minus 3. Okay. This value, shabab, is very close to the zero. We said X is greater than or equal to 0 and less than or equal to 1. It is equal to 0 at saturated liquid, it is equal to 1 at saturated liquid. So when the value of X is close to 1, that means we have more gas. If it is close to 0, that means we have more fluid. So the value here is very low, that means we have more fluid in this case. Only we have a small portion of the gas. Okay. But in this case, we have calculated X2. So at this temperature also, we can get U fluid and we can get also U gas at this temperature from table A4. Then using this X2, we can say U2 will equal to U fluid plus X2 multiplied by U gas minus U fluid. Or you can just say U gas minus U fluid is UFG. And you can read this value directly from the table. Okay? We have all values, then we can calculate the value U2. If you calculate U2, it will equal to 104.88 kilojoule per kilogram. Okay. Then we can apply the first law of thermodynamics to calculate the heat transfer. U minus work is equal to mass multiplied by specific energy U2 minus U1. But in this problem, we have rigid tank, and we have a diaphragm, and we have water, and we just added heat. Do we have any kind of work here? Do we have boundary work? Is this a piston cylinder device and one of the boundaries is moving? We don't have in this case piston cylinder device, so we don't have boundary work. Do we have shaft, power, paddle wheel or something, or we do have electrical heat supply? We don't have. So in this case, actually, we don't have any kind of work, so the work is equal to 0. So the heat transfer will equal to mass multiplied by U2 minus U1. Mass is 5. And the specific energy U2 is equal to 104.88 minus the specific energy U1, which is 104.87. And in this case, we can calculate the heat transfer. This is kilojoule per kilogram, and this is kilogram, so the heat transfer will be kilojoule. It will equal to 0.25 kilojoule. And this is actually the amount of heat transfer in this process. Okay. We need also to represent this process. We can represent it actually on the PV diagram. So at state number 1, pressure V1 is given, temperature T1 is given, and the state is subcooled. So at state number 1, this is the pressure, specific volume diagram, and this is the saturation curve. Point 1 was subcooled here. This is point 1 at 200 kilopascal. Okay. Now, at state number 2, the pressure has reduced down to 3.16 something. So the pressure has been reduced, and the state is saturated mixture. So in this case, we can just say this is actually state number 2, and the process actually is just from state 1 to state number 1 to state number 2. Pressure at state number 2, 3.6 something kilopascal. As we said, the quality is very close to 0. So that means actually we have more the mixture consists mainly of the fuel, and we have a small portion of the gas. So point number 2 should be close to the saturated liquid curve. So point number 2 should be something here. Okay, if X is high, very close to 1, then in this case we have to be close to the saturated vapor line. يعني this is يعني a sketch, you are not writing here to scale or something. Okay. طيب this is يعني an example يا شباب. Here is another example also. Let's go through. In this example, we have water in a piston cylinder device. Okay, well, in this example, we have a frictionless piston cylinder device shown in the figure. This is actually equipped with a stop, and it actually contains 0.9 kilogram of water. So here we have water in a piston cylinder device. This piston is frictionless piston, and it is actually standing on the stops here. And inside this tank, actually we have water. The mass of this water, mass here, is equal to 0.9 kilogram. He said initially the piston actually sits or resting on the stops when the value of the water temperature, so the temperature T1 is equal to 150 degrees C. Okay. Now he said actually the heat is added to this water. So in this case, the temperature of the water will be raised and the pressure will be raised in this case. But this piston shabab has weight. Okay, with this weight actually is equal to mass multiplied by gravitational acceleration. They said this piston will be start to move when the pressure V2 is equal to 600 kilopascal. Okay, so this piston is frictionless piston, but it is heavy one. So when we add heat, the temperature of the water will be raised and the pressure will be raised. But still this pressure cannot actually overcome the weight of this piston. So we continue adding heat. So this piston will start to move when the pressure value equal to 600 kilopascal. So in this case, when the pressure equal to 600 kilopascal, there should be a pressure force acting upward equal to pressure multiplied by area. This will be actually equal to what? The weight of this piston at step number 2. So in some cases, actually, he may give you the mass and the gravitational acceleration, and he asks you to calculate the pressure at which this piston will start moving. So this pressure, V2 multiplied by area of this piston, should equal to mass multiplied by gravitational acceleration. He may give you the mass of this piston and give you the cross-sectional area. Then we can calculate the pressure V2. But in this case, he gave it directly. So maybe I will do it in one of your exams. Okay. So the pressure at state 2, at which the piston will start moving, is equal to 600 kilopascal, and he said the quality of the water in this case is equal to 80%. Quality 80%, that means actually X2 is equal to 0.8 in this case. And he said we continue adding heat actually until we reach a final temperature T3 is equal to 200 degrees. So we continue raising the temperature, continue adding heat until the temperature T3 is raised actually to 200 degrees. First of all, we need to represent this process on the TV and PV diagram. We need to calculate actually the work, and we need to calculate actually the heat transfer out of this process. But this process, shabab, when we add heat from state 1, at temperature equal to 150, I will be adding heat. Then in this case, the pressure will be raised and temperature will be raised. But actually, this piston is just sitting on the step until we reach this value of pressure at which the piston will start moving. Okay, so from state 1 up to state 2, the piston is resting on the stop. That means actually the volume V1 is the same as what? The volume V2. As the mass is constant, so we can say specific volume V1 is the same as a specific volume V2. And the process from state 1 to state 2 is a constant volume process. Now he said this piston is frictionless piston. When this piston start moving at this value of pressure, it will be free movement. So free movement يا شباب means what? That the pressure will be remaining constant. So pressure B2 is the same as what? Same as pressure B3. So let's represent this process on the TV diagram with respect actually to the saturation curve. We have process from 1 to 2 is actually constant volume process. Specific volume V1 is the same as a specific volume V2. But at state number 2, we have the quality is equal to 80%. That means at state number 2, we are within the saturation zone. But at state number 1, the pressure actually should be at lower value compared to state number 2. So when we add heat, the pressure is raised. So let's say this is actually state number 1 at lower pressure. When we add heat, the pressure actually will be raised, and we will reach actually state number 2 within the saturation mixture zone. As the quality X2 is given, so we are within the saturation zone. But after state number 2, I will be adding heat under constant pressure line on the TV diagram at state number 2. So this line represents a line of constant pressure. So in this case, I will be adding heat. So the gas actually will be expanding, the volume will be increasing in this case, following this constant pressure line until we reach actually state number 3, which should be actually superheated in this case. Because at state number 3, pressure is equal to 600, temperature is equal to 200 degrees C. Under this condition, the state should be superheated. Anyway, we'll check this actually while the solution. Also, we can represent the process on the PV diagram. It will be something similar. This is a PV diagram. State 1 process from 1 to 2 under constant volume. And this is actually a line of constant pressure on the PV diagram, just a horizontal line until we reach state number 3, which lies within the superheated zone. Okay. Type we need to calculate in this case, in this problem, we need to calculate the work. So in this case, do we have electrical work, شباب? Do we have shaft work? We don't have. But we have a gas in a piston cylinder device, and one of the boundaries is moving in this case. So we have boundary work. But for process from 1 to 2, this process actually is a constant volume process. Still, the piston is not moving. So this means the boundary work for the process, from 1 to 2, which equal to the boundary work, which is integration of BdV. The volume is constant in this case. So in this case, the boundary work for the process from 1 to 2 is 0. Okay, but what about process from 2 to 3? We have constant pressure process, piston free movement. So the pressure from state 2 to state 3 will equal to the boundary work, will equal to the pressure multiplied by mass, multiplied by specific volume, actually V3 minus V. This is actually for the process from 2 to 3, which is actually a constant pressure process. Okay. So how we can calculate this work? We have the pressure is given, and we need to calculate actually the specific volume at state number 2 and the specific volume at state number 3. The working fluid here is water, so I will be using steam. So at state number 2, we have pressure D2 is equal to 600 kilopascal, and we have in this case the quality X is equal to 0.8 in this case. So in this case, to calculate the specific volume D2, I will be going to table pressure, I will be going to table A5, I will get the value of V fluid and the value of V gas in this case. They said it is already saturated mixture as the value of X is given. Then we can say V2 will equal to V fluid plus X2. This is X2 multiplied by V gas minus V fluid. Then we can calculate the specific volume V2. You can check the numbers here. Specific volume V2 will equal to 0.2527 meter cube per kilogram. Okay. Type this is V2. What about state number 3? State number 3, we have temperature T3 is equal to 200 degrees C, and the pressure V3 is the same as V2, which is 600 kilopascal. Pressure and temperature are given. You can take this pressure, go to table A5, Then from table A5, I will get the saturation temperature at this pressure. You will find here that the given temperature is greater than the saturation temperature. So the state is superheat, and I have to use table A6. Using table A6 with this pressure and temperature, pressure is equal to 0.6 megapascal, and temperature T3, we can get the specific volume V3. Specific volume V3 will equal to, in this case, 0.352 meter cube per kilogram. At step number 3, Shabab, also, we will be needing actually the internal energy U3, as we need to calculate also the heat transfer. So we will apply the first law of thermodynamic equation, Q minus work will equal to delta U. Then at this case also, we can get the value of U3 from the table at this pressure and this temperature. The value of U3 will equal to 2639.4 kilojoule per kilogram. Okay. Then come here. We have a specific volume V3. We have a specific volume V2. We have the pressure, which is from 2 to 3 is fixed to 600 kilopascal, multiplied by the mass, which is 0.9, multiplied by V3, 0.352, minus specific volume V2, 0.2527. Then we can calculate, in this case, we can calculate the boundary work or the work from state 2 to state 3. It equal to 53.68 kilojoule in this case. And this is actually the work from state 2 to state 3. Work from state 1 to state 2 is 0, as the process actually, as the process is constant volume from state 1 to state 2. But we need to calculate also the heat transfer. We have two processes in this case. So we can just apply the first law of thermodynamics. We can just say Q minus work will equal to M multiplied by U final minus U initial. So in this case, we can consider for the whole process, we can consider the whole process Q from state 1 to state 3 minus work from state 1 to state 3 should equal to mass multiplied by U3 minus U1. Okay? Or we can do something else. We can just say Q from state 1 to 2 minus work from state 1 to 2. That will equal to mass U2 minus U1. And we have another process, Q from state 2 to 3 minus work from 2 to 3. That should equal to mass multiplied by U3 minus U2. And then to calculate the total heat transfer, we have to add up actually those two terms from those two equations. Then we can calculate the total heat transfer. Or we can just simply consider the whole system from state 1 to state 3. So Q from 1 to 3, which we need to calculate, will equal work from 1 to 3. Work from 1 to 3 is the work from 1 to 2, plus the work from 2 to 3. Work from 1 to 2 is equal to 0, constant volume process. And work from 2 to 3, we just calculated here, which is equal to 57.68 kilojoule. Okay, mass here is equal to 0.9 kilogram. U1, we have already calculated, U3 minus U1. U3 we just get here from the superheated table A6, which is this value. Okay, 2639.4. But what we need to calculate here actually is the internal energy U1. Okay, how we can calculate it? So the internal energy U1, we have at step number 1, the temperature is equal to 150. But do we have another property at step number 1? Yes, we have a specific volume V1 is the same as V2. We have calculated already V2 to calculate the boundary work. Then at step number 1, T1 is equal to 150 degrees C, and the specific volume V1 is the same as V2, which is 0.2527 meter cube per kilogram. Okay. Then with this temperature and the specific volume, we can go to table A4. Specific volume, then I will get free fluid, and also I will get the value of a specific volume V gas. And to compare it with this specific volume, you will find actually that the specific volume V1 is greater than V fluid and less than V gas. So the state is saturated mixture. And in this case, to calculate any property, we need to calculate the internal energy. Then in this case, I have to calculate X. So X1 will equal to V1 minus V fluid divided by V gas minus V fluid. We have V gas and V fluid and V1, then we can calculate the value of X1. If you calculate this, the value of X1 will equal 2.64 fluid, and this is the quality X1. We need to calculate U1. So from this table, in this case, at the temperature T1, we will be calculating also, in addition to UV fluid and V gas, I will get U fluid, and also I will get the value of U gas at this temperature T1. Then U1 will equal to U fluid plus X1 multiplied by U gas minus U fluid, or UFG, we can get it directly from the table. Okay? If you calculated it, so it will be actually U1 18 equal to 1870.7. This is actually kilojoule per kilogram. And this is the value of U1. Then come and substitute here by U1, so we can calculate the heat transfer for the whole process from 1 to 2. So in this case, the heat transfer will be calculated. Q actually from state 1 up to state 3 will equal to 745. This value will equal to 745.5 kilojoule. Okay, and this is actually the total heat transfer calculated in this case. Okay, so Shabab, the idea here for this problem that we have actually a heavy piston. We will add heat, the pressure will rise, but the piston is not moving. Until we reach a given value of pressure, the piston will start moving. So the process actually from state 1 up to state number 2, in this case actually will be constant volume process. We have V1 is the same as V2. But when this piston starts moving, in this case it is a frictionless piston. He said it is a frictionless piston. So in this case actually the pressure will be remaining constant. In this case V3 will be the same as V2. And this is the key for the solution of this problem. Okay. Let's stop here today. And let's inshallah continue next time.